Hi, welcome to part 9 of the video series about laws of motion. The normal force is the force exerted by the surface on an object in contact with it. It is acting perpendicular to the surface, irrespective of whether the plane is horizontal or inclined. The phrase normal in this instance is used in the geometric sense and means perpendicular, as opposed to the common language use of normal meaning ordinary or expected. We have stated that normal force is always perpendicular to the surface, so let's see how we can draw it depending on the surface. In the first diagram, an object is on a horizontal surface. To represent the normal force, we draw a vector which starts at surface and acts towards the object. In the second diagram, the object stands on an inclined surface. The normal force is the vector which starts at surface, perpendicular to it, and which is drawn towards the object. In the third diagram, the object is standing or sliding on a surface which is in a vertical direction. In this case, the normal force will be in horizontal direction, as it must be perpendicular to the surface. In the last diagram, the object is touching the ceiling. A magnet attached to a metallic ceiling can be an example for this case. Again, the vector representing the normal force starts at surface and points towards the object. At the same time, it is perpendicular to the surface. Calculating the value of the normal force can differ depending on the type of the question. In this video, we are going to learn how to calculate it for the easiest three cases. In first example, an object of mass of 5 kgs stands on a horizontal surface. The task is to calculate the normal force applied on this object. As usual, for most of questions in laws of motion, we start our solution by drawing a free body diagram for a given object. There are two forces applied on the object on the figure. Force of gravity is acting downwards and the normal force is acting upwards from surface towards the object. The object is in equilibrium, at least for the vertical axis. The reason we say at least in vertical axis is that the normal force is in vertical direction. So while calculating it, we will deal with vertical forces only, or the forces which are parallel to it. If we choose upwards as a positive direction and downward as a negative one, the normal force will have positive value and the gravitational force will have a negative one. Force of gravity is equal to mass times gravitational acceleration, which are 5 kgs and 9.8 meters per second square respectively. The normal force is equal to 49 newtons. In the second case, we have same object on the same surface. It is experiencing one extra force, a force of 10 newtons which is pressing the object to the surface. As usual, let's start the solution by drawing a free body diagram. First two forces in the diagram are same as in the previous question. The force of gravity is downwards and the normal force is upwards. The last force is the force shown in the figure in the question. A force of 10 newtons applied downwards. Again, while calculating the normal force, we only consider the forces which are parallel to it. If we choose upward as a positive direction, the normal force will have positive value, force of gravity and applied force will get a negative one. Force of gravity can be calculated by multiplying the mass of the object and the gravitational acceleration. Mass is 5 kilograms, gravitational acceleration is 9.8 meters per second square, and the applied force is 10 newtons. The normal force for this question is going to be equal to 59 newtons. The last example of this video is very similar to the second one. The only difference is the direction of the applied force. In a free body diagram, we draw the force of gravity and the normal force as usual. For applied force, we will just swap its direction. Instead of drawing it downwards, now we will draw it upwards. As a result, in the equation, it will have a positive value as opposed to its value in the previous question. So, the equation becomes normal force plus 10 minus 5 times 9.8, and it is equal to 39 newtons. In the fourth case, there is a 10 Newton force pushing the object, but this force makes 37 degrees with the horizontal. The task is to calculate the normal force applied on this object. As usual, we start with drawing a free body diagram for a given object. First two forces which we will draw are force of gravity and the normal force. We can recall that the normal force is always perpendicular to the surface. While calculating it, we will need to consider only the forces which are parallel to it. In other words, perpendicular to the surface. That's why, while drawing the applied force, instead of drawing it in the direction shown in the question, we will resolve it into its components, Fx and Fy. From the diagram, we can see that Fx will have zero effect in calculation of the normal force, as it doesn't have any value in vertical direction. As a next step, we can write the formula stating that the net force on a y-axis is equal to 0, as object is not accelerating up or down. If we choose upward as a positive direction, the normal force will have a positive value, force of gravity and Fy are going to have a negative value. Force of gravity can be calculated by multiplying mass and gravitational acceleration. Fy is opposite to 37 degrees, so its value can be calculated by the formula F times sine 37. Mass is 5 kilograms. Gravitational acceleration is 9.8 and force is 10 newtons. The normal force will be equal to 55.02 newtons. The only difference in case 5 is the direction of applied force. That's why the solution is also going to have a small difference. In a free body diagram, we draw the force of gravity and the normal force, while resolving the applied force F into its components. Opposing to the previous question, Fx will point to the left and Fy will point upwards. Net force on a y-axis is 0 again. We choose upward as a positive direction, so this time Fy is going to have a positive value as well. The only force which is going to have a negative value due to pointing downwards is the force of gravity. Fy is equal to F times sine 37 and force of gravity mass times acceleration. F is 10 newtons, mass is 5 kilograms and G is 9.8 meters per second square. The normal force is equal to 42.98 newtons. The explanation of the last example in this video may seem a bit complicated, especially if you don't like geometry. But at the end of the day, the only thing you will need to know is one formula, which you can memorize and use anytime you need without even thinking about the explanations we will see. The task is to calculate the normal force on a 5 kg object resting or sliding on an inclined plane. Let's start solution with drawing a free body diagram. There are two forces applied on this object. Force of gravity acting downwards and the normal force acting perpendicular to the surface. Of course, there can be friction force, but it will have no effect on our solution. If you still expect to see this kind of questions which includes a friction force as well, don't worry, we will cover them in the videos related to friction force. As we mentioned in the previous examples, to calculate the normal force, we only need the forces which are parallel to it. In other words, which are in the same direction or opposite to it. To achieve this, we can resolve the force of gravity into its components. As these components will not be in the direction of x or y axis, it's better to name them Fg parallel for the component which is parallel to the surface, and Fg perpendicular for a component which is perpendicular to the surface. Net force of vectors perpendicular to the surface is equal to 0, which means the magnitude of the normal force is equal to the magnitude of the perpendicular component of force of gravity. To calculate the value of the normal force, we just need to calculate the value of this perpendicular component. To be able to do it, we will get some help from geometry. If the angle at the bottom of a right triangle is 37 degrees, the angle at the top will be 53 degrees. By using similarity, we can see that the angle between Fg and its parallel component is 53 degrees as well. As the angle between two components is 90 degrees, the angle between force of gravity and its perpendicular component is going to be 37 degrees. As Fg perpendicular is adjacent to 37 degrees, its value can be calculated as force of gravity or mass times gravitational acceleration multiplied by cosine 37. Mass of the object is 5 kilograms. Gravitational acceleration is 9.8. The magnitude of the normal force exerted on this object is 39.13 newtons. Imagine we enter a lift and try to go to a higher level. Let's try to recall the feeling we are experiencing just when lift starts to move upwards. We feel ourselves getting heavier. On the opposite side, at the instant the lift starts to move downwards, we feel ourselves getting lighter. Hopefully, examples in this video will set light to this phenomenon. In the first example, a lift is accelerating upwards at an acceleration of 2 meters per second square. The mass of the object is 5 kilograms. We start with solution by drawing a free body diagram for this object. By doing so, we isolate the object and make the solution to seem much easier. There are two forces applied on this 5 kilogram object. Force of gravity exerted on it by Earth and the normal force exerted on the object by the surface of the scale. According to the second law of motion formula, the net force applied on the object is equal to the product of the mass and acceleration of the object. As object moves upwards, we consider upwards as positive and downwards as a negative direction. We can rewrite the equation as normal force minus force of gravity is equal to mass times acceleration. Force of gravity can be calculated as mass times gravitational acceleration, which are 5 kilograms and 9.8 meters per second square respectively. As mentioned in the question, acceleration of the system is 2 meters per second square. After calculations, we can get that the normal force exerted on the object is equal to 59 newtons. By standing on it, we are compressing the scale, and what the scale actually reads is the force that is compressing it. By the Newton's third law, the scale is pushing back on us with the same force, which is the normal force we have just calculated. Even though it is a very confusing term, sometimes this force is also known as an apparent weight. I will not dive deeper into it as it may confuse most of us, but put simply, there are two types of weights. The first one is the actual weight, which is the force exerted on an object by a planet, and which can be calculated by multiplying mass and gravitational acceleration. The second one is the apparent weight, which for this type of questions has same magnitude as the normal force exerted on the object. In the second example, the same object is now in a lift which accelerates downwards. The task is the same, to calculate the normal force or reading on the scale. As usual, let's start by drawing a free body diagram. we draw the force of gravity and then the normal force. Then, to get our first mark, we continue the solution by typing the formula. Net force is equal to mass times acceleration. By convention, we will consider direction of motion as a positive direction. The system is moving downwards, which means for this question, force of gravity will have a positive value and the normal force will have a negative value. Force of gravity is mass times acceleration. After substitution, 5 times 9.8 minus the normal force is equal to 5 times 2. The normal force and the reading on the scale is going to be 39 newtons. The third question is the interesting one. Everything is the same as in the previous question, but the acceleration of the lift. This time, it has the same value as gravitational acceleration, 9.8 meters per second square. We will go through the same steps. Draw a vector downwards to represent the force of gravity and another one upwards to represent the normal force. Then, to make sure that we get full marks, we will write down the formula. Consider downwards as positive as object moves downwards. Finally, we do substitutions. Mass of the object is 5 kilograms, and then both gravitational acceleration g and acceleration of the system A have the same value, 9.8. The normal force exerted on the object is equal to 0, which means the reading on the scale is 0 as well. The object is weightless, and this phenomenon is known as weightlessness. I pray that no one will experience it. The cables holding the lift are broken and it falls down with everything inside it. In that moment, objects will not be able to compress the scale, so the reading on the scale will remain at 0. We are not going to solve a question about it, but can you guess what will happen if the lift falls down with a greater acceleration than the gravitational acceleration of 9.8, let's say at 15 meters per second square? Yes, you are right. In that case, we will stick to the sailing. In other words, the sailing will become a flow for us and we will be able to walk on it. The next question is also a tricky one. We may get it wrong unless we read it properly. The lift is still moving downwards, but this time, instead of 2 meters per second square, the value provided is 2 meters per second. As we recall, meters per second is the unit of velocity, not acceleration, meaning the acceleration of the system is equal to 0. If we follow all the steps again, draw free body diagram, then write down the formula for the second law of motion, extend the formula by determining the downwards as a positive direction, and then do substitutions. The normal force is equal to 49 newtons. Let's finish this video by one more tricky question. A lift with a scale and object on the scale moves upwards, but at the same time it slows down. What will be the reading on the scale? We should already get used to starting to solve this kind of questions by drawing a free body diagram. Force of gravity is acting downwards and the normal force is acting upwards. The lift is moving upwards, which means we will consider upward as a positive direction. The normal force will have a positive value and the force of gravity will have a negative value. The force of gravity can be calculated as mass times gravitational acceleration. The tricky part of this question is hidden in substitution part. In grade 10, we have learned that if an object is speeding up, the direction of velocity of the object and its accelerations are same. And if an object is slowing down, the direction of the velocity of the object and its acceleration are opposite to each other. The lift is slowing down, which means velocity and acceleration are acting in opposite directions. We have already considered the direction of motion or direction of velocity as positive, which brings us to conclusion that the direction of the acceleration must be negative. You may ask why we didn't write minus in front of gravitational acceleration. We already did it. The minus in front of mass times gravitational acceleration belongs to g. As a result, the normal force is equal to 39 newtons. Don't forget to subscribe and turn on the notifications in order to be updated about my new videos.